In this video, we will talk about the inductive and resonance effects on electrophilic aromatic substitution reactions. Specifically, we'll talk about activating groups and activating groups as ortho-pair directors, deactivating groups and deactivating groups as meta-directors. We'll talk about halogens as deactivating ortho-pair directors, and then end with the directing effects of multiple substituents. So an activating group is when a substituent that is already present on benzene makes it more reactive in electrophilic aromatic substitution. So in this case, G is our group that is already on the benzene ring, and now this benzene ring is going to react with another electrophile. Okay, so G is already present. So G's presence is going to make benzene more reactive than it would be on its own. So now the pi electrons that are going to go and attack the electrophile, this is going to be a faster reaction than would normally occur. Okay, so G is essentially helping out the benzene ring and kind of pushing those pi electrons to attack the electrophile. Okay, then EAS would continue here. Okay, so it's promoting the formation of our rhenium ion intermediate. So let's take a closer look at how activating groups work on the next slide. The rate of EAS reactions, so how quickly they occur, is completely dependent on that first step, the formation of the rhenium ion intermediate. So the way that activating groups are going to work is activating groups actually donate some electron density to the ring. Now by donating electrons, what they're going to do is they stabilize the developing rhenium ion, which is positive. Now, if that positive charge is stabilized, it's going to make it more likely to form. So this is going to make the ring more reactive. Now, this is known as the inductive effect. Where the group already attached to the ring can influence the rate of the reaction. Now, examples of activating groups. They can include amino groups. So it would be attached to the ring here. So a nitrogen portion of this group can act as an activating group. You can have hydroxyl groups, which act as activating groups. Now these are also known as electron donating groups. Or EDGs. So table 18.1 in the book, which I've also posted on Canvas, has a list of activators and deactivators by category. So we're going to focus on the activating groups here. Now they are broken down into three main categories. We have strong activators, moderate, and weak activators. So I'm just going to point out some features that can help you distinguish between an activating group and a deactivating group, which we're going to learn about in just a little bit. So for activators, I want you to pay attention to the atoms that are directly connected to the benzene ring. So we have oxygen here, oxygen, nitrogen, nitrogen, nitrogen. All of these atoms contain lone pairs. So those lone pairs are capable of being donated to the ring. Okay, so they can donate those lone pairs, they can stabilize that uranium ion, which is going to make them activating groups. For moderate activators, we also have oxygens and nitrogens, but you'll notice that we have them connected to carbonyls. So in addition to the electrons being donated to the benzene ring, they're also participating in resonance with this carbonyl. So that's going to make this arrow a little bit smaller. Show it teeny tiny. So there's going to be less of that electron density going towards the ring because more of it's going towards the carbonyl. So that's going to make it a little less strong than just our regular strong activators. Now this guy is the exception. So typically in other books, this is considered a strong activator. For our purposes, we'll consider this a strong/moderate activator. And then finally, we have weak activators. So those are R groups. Now R groups themselves do not have lone pairs that can be donated to the ring, but they are capable of donating electron density. Okay, so R groups are weak activators. Now, activating groups are known as orthopara directors. And what this means is if we have an activating group attached to the benzene ring, any sort of incoming group that's going to be attached will go to either the ortho or the para or the para position. So ortho would be right next to the activating group, meta would be one carbon away, and para would be on the opposite side of the ring. So all incoming groups will go to the ortho and or para position. Now this type of directing that activating groups are capable of participating in is known as the resonance effect. And the reason it's the resonance effect has to do with the rhenium ion intermediate, which we'll see on the next slide. So let's take a look at an example. If we were to have a benzene ring with an OMe group attached, now this is considered an activating group. So not only is it going to make another EAS reaction go faster, but it's going to direct any incoming group to the ortho or para position. So if we were to take this benzene ring and react it with halogenation conditions to install a chlorine, the chlorine can go either ortho to the OMe group or para. And most often you do get a mixture of products. Now let's take a look at why the chlorine is only going to go to these positions and not to the meta position, looking at the resonance structures. Let's first take a look at the ortho substitution of the chlorine on the benzene ring. Now we already have our methoxy group attached to the benzene. We have the electrons on the oxygen, which can be donated to make the reaction occur a little bit faster. Now, when this benzene comes into contact with the electrophile that forms for chlorination, which is this structure here, the pi electrons are going to go, grab the chlorine at the end, and give the electrons to the other chlorine. Now we're focusing on ortho substitution here, so we want to make sure that the chlorine goes in the ortho position and the rhenium ion on the other position. So we have our first resonance structure. Now we know that we have an allylic positive charge that can participate in resonance, so we'll go ahead and draw our second resonance structure here. Then we have another positive charge. That's allylic. So we will form our third resonance structure. Now, we have a positive charge that's next to a lone pair. The oxygen from our methoxy group can actually donate its electrons down to form a fourth resonance structure. So it's going to share some of that positive charge amongst a fourth atom. So this fourth resonance structure is a stable contributor to the uranium ion hybrid. And the fourth resonance structure is what's going to make orthosubstitution so much more favorable than the meta-substitution, as we'll see in just a second. So we've got our fourth resonance structure here. Let's go ahead and just show the last step of this mechanism to restore the aromaticity. So the iron will kick off the chloride. The electrons will go in the direction of the positive charge and will kick up the electrons up onto the oxygen atom. And we've completed adding another substituent to our ring. Now with para substitution and activating groups, you're going to see the same fourth resonance structure. And I do invite you to try that on your own just so you can see. Now let's take a look at meta-substitution with an activating group. And we'll see why this is not favorable. Okay, so we're starting with the same benzene with the methoxy group. We have the same electrophile. Our benzene will go and take the chlorine. Now we want to focus on meta-substitution, so we'll place the chlorine at the meta position. And the carbocation at the other position. Okay, so we have our first uranium ion resonance structure. Now this is an allylic cation, so we'll have the electrons come over. We form our second resonance structure. And then we've formed another allylic cation. Which is going to form here. Now, at no point is the positive charge going to end up on the carbon containing our activating group. So there's no way for us to form the fourth resonance structures. So in meta-substitution with an activating group, only 3 resonance structures contribute to the uranium ion. And for all chemical reactions, the more resonance structures you have, the more favorable that reaction is. So more resonance is more favorable. Less resonance, less favorable. Okay, so since meta-substitution has less resonance than the ortho or para, it's going to make the meta-substitution a lot less favorable. An ortho-para director is capable of directing an incoming group to either the ortho or the para position. So how do we decide which one is going to be the major product, the ortho or the para? So it's important to note that both products will form. Now, in general, we take a look at the size of the group, the ortho-para director, to determine whether or not it's going to be an ortho or para major product. Now, a small group, such as this methyl group here, will form the ortho and the para product, and it's not very easy to determine which one is going to be major. So in general, we will get a mixture of products when we have methyl as our activating group. So on a quiz or exam, it would be important to draw both products. However, if we use a bulkier group, such as this tert-butyl group, there's a lot of steric hindrance involved with this group. So even though we will form the ortho and the para products, we're very confident that the para is going to be our major product because there's too much steric hindrance with the tert-butyl group and the ortho position. So for the most part, for most groups, except for methyl, the para will dominate over the ortho product. Now, if you're unsure about which one is going to be the major product, you can always just draw both. Now, deactivating groups are kind of the opposite of activating groups. And a deactivating group is when a substituent that's already present on the benzene ring makes the benzene ring less reactive in electrophilic aromatic substitution. So a deactivating group actually withdraws electrons from the benzene ring. So it's going to pull either electron density or actual electrons through resonance away from benzene. Now what this is going to do is it's going to cause a slightly positive charge to start to form at the base of the carbon attached to the deactivating group. So as this deactivating group withdraws electrons from the ring and creates a slightly positive charge, the slightly positive charge is going to clash with any sort of additional positive charge that's going to form from the uranium ion. So this clashing of positive charges actually destabilizes the developing uranium ion. If the ring has already had electron density taken away from it, it's going to be less likely to have the pi electrons go out and act as nucleophiles, because again, we're giving up the electrons and creating more positive. So as we're destabilizing this developing uranium ion, it's going to make the ring less reactive. And all of this is related to the inductive effect. Now, examples of deactivating groups can include carbonyls, and these would be carbonyls directly connected to the benzene ring. So this carbonyl is an electron withdrawing group, also known as a deactivating group. You can also have electronegative atoms, so carbon with 3 fluorines attached. The fluorine is a highly electronegative atom, so it's going to pull the electron density towards itself. And the halogens, so fluorine, chlorine, bromine, or iodine, are all included as examples of deactivators. So here's another portion of Table 18.1 that's focused on deactivators. Now again, they are listed in terms of weak to moderate to strong deactivators. So let's go ahead and take a look at the trends that we see. So our weak deactivators are the halogens. So the halogens are not capable of resonance. Chlorine is somewhat electronegative. Bromine and iodine are very large, so they're capable of taking electron density towards themselves as well. But since we don't have set resonance, it's going to make them weak deactivators. Our moderate deactivators all have resonance capabilities. So you'll notice that attached to the benzene ring, we have a carbonyl. In all of these examples, we also have resonance capabilities with the sulfur that's double bound to oxygen. And then a carbon that is triple bound to nitrogen is also capable of resonance. So those are all considered our moderate deactivators. Our strong deactivators are going to be considered a nitro group, and a nitro group actually has resonance. A nitro group has this structure. Now, the reason that this group is a much stronger deactivator than the moderate deactivators is because you have 3 highly electronegative atoms. So those are themselves going to pull electrons towards themselves, but we also have resonance in addition to that. Anytime you have a nitrogen with a positive charge, this positive charge can also attract electron density, so that's going to make it a strong deactivator. And when you have a carbon attached to 3 halogens, it's also going to be a strong deactivator, again pulling the electron density towards these halogen groups. Now the deactivating groups, except for the halogens, are all meta-directors, and we'll talk about the halogens on the next slide. Now for our meta-directing deactivating groups, let's go ahead and take a look at a benzene ring substituted with a strong deactivating group, CF3. Now again, the electronegativity of fluorine is going to pull the electron density towards this group. So we're going to have a slightly positive charge that's starting to form on this carbon. Now that's going to make the benzene ring slightly slower in electrophilic aromatic substitution than just a regular benzene ring normally would, but it can still react in some cases. So let's go ahead and react this with a halogenation reaction. We'll focus on the electrophile after it's already formed. And we're going to focus again on the uranium ion resonance structures. So our pi electrons from benzene are going to come in, grab the bromine, and give the electrons to the positively charged bromine. Now we are focusing on meta substitution, so we're going to go ahead and place the bromine at the meta position. And the uranium ion is going to be placed at the other position. Now let's go ahead and focus on the resonance structures. So we have an allylic cation, so you can have the pi electrons come over. We get the positive charge here. And then we have another allylic cation. To form our third structure. So unlike the ortho-para directors, we don't get a 4th resonance structure. However, we get 3 resonance structures where the positive charges do not overlap at any point. So the carbons that all get the positive charge are different from the one that continually has that partial positive charge. So as a result, with the meta-substituted resonance structures, we have no unstable resonance structures. Now let's go ahead and take a look at what would happen if we were to do an ortho substitution with this deactivating group. And this one's meta substitution. Okay, so we'll start with the same group. Again, we know that it is a deactivating group, pulling the electron density. And if we were to react it with the same electrophile, but now place the bromine at the ortho position, let's go ahead and take a look at the resonance structures. So we have an allylic cation coming over. Then another allylic cation. And in our third resonance structure, we see that we have a positive charge on the carbon containing our deactivating group. Now, this carbon originally had a slightly positive charge, and it's going to maintain that slightly positive charge because this is an electron withdrawing group. So we have a positive charge on top of a partial positive charge that is too much positive for that atom to take. So this is actually a highly unstable resonance structure because you have the clash of like charges. So with ortho substitution, and it's also going to be the same with para substitution. We end up with a highly unstable resonance structure. So as a result, we would really only end up with 2 resonance structures, and we know that more resonance structures are going to be better for the molecule as a whole. So for deactivating groups, except for the halogens, we would always get the meta direction because we would end up with 3 stable resonance structures for the uranium ion intermediate. Now let's go ahead and take a look at the halogens. Although the halogens are deactivating groups, they are orthopara directors, and those have to do with the 2 different effects that we have with electrophilic aromatic substitution. So the fact that the halogens are deactivating groups is part of the inductive effect. And the inductive effect is going to influence reaction rate. So the halogens will make the rate of an EAS substitution a little bit slower because of the fact that they're deactivating groups. However, the fact that they are orthopara directors has to do with the resonance effect. Okay, and the resonance effect influences the incoming group's position. So let's go ahead and take a look at halogens as orthopara directors. And we will use bromine as our halogen, and we will show it performing a second halogenation, adding a chlorine to the ring. So we have our super strong electrophile. We will have the pi electrons coming and attacking the chlorine, giving the electrons to the positively charged chlorine. Now we are going to focus on ortho substitution because halogens are orthopara directors. Now right away we can see a positive charge on the carbon containing our halogen. Now halogens have lone pairs. So similar to what we saw with the activating groups, these lone pairs can be donated down to create a 4th resonance structure. So we can share that positive charge with the halogen. Now at this point, we can continue showing the uranium ion going around the ring. We will have the pi electrons here come over to form a double bond and kick the electrons up onto the halogen. So now we have the uranium ion back on the ring. Then we will get one more with our allylic positive charge. I'll go ahead and draw it down here. To complete our 4 resonance structures. So similar to what we saw with the activating groups as orthopara directors, halogens are also orthopara directors because we get the 4 resonance structures. So this is table 18.1 in its entirety. So it is listed by activators and deactivators, but it also includes their directing ability. So this is our cutoff for activators and deactivators. So we have our weak, moderate, and strong activators, and our weak, moderate, and strong deactivators. Then over here, this is the cutoff for the directing ability. So anything below this line, the moderate or strong deactivators, are meta-directors. Anything above this line, including the halogens and all of the activators, are orthopara-directors. So this table is key, and I have provided it on Canvas for you to print out and use with your homework and any other practice problems you are doing. So let's go ahead and do a set of practice problems where we predict the major products. As always, you're welcome to pause the video, attempt it on your own, and then come back and check your answers. So we want to look at two things with these problems. We want to look at the substituent that's already attached to the ring, and we want to determine what its directing effect is, whether or not it's an orthopara or meta-director. Then we also want to look at the type of reaction this benzene ring is undergoing to see what the new substituent is going to be. So for our first problem, we have this group attached to our benzene ring. Now, even though it contains a carbonyl, and we typically associate carbonyls with deactivating groups or meta-directors, this carbonyl is not directly connected to the benzene. So let's go ahead and focus on this oxygen atom. Now, oxygen has two lone pairs that we can go ahead and draw in. Now, the fact that we have an oxygen with lone pairs attached to our benzene ring, it's going to make it an activating group and an orthopara director. You can also use table 18.1 to help you with that. Okay, so we know that any incoming group will go to either the ortho or the para position, or both. So now let's go ahead and take a look at the reagents. We are reacting the benzene with chlorine in the presence of a Lewis acid catalyst. So this is going to be a halogenation. And we're installing the chlorine on the benzene ring. So let's go ahead and draw the products of both the ortho and the para substitution. Now we're simply asked to write the products. We don't have to worry about the mechanism. So I will get one product where we have the chlorine at the ortho position and one where it's at the para position. Now in terms of major products, this group is fairly bulky and it would introduce a fair amount of steric hindrance at the ortho position. So we can guess that the para substituted product is going to be the major product because it has the least amount of steric hindrance. Now in our second problem, focusing on the group we have attached to the benzene. So this time we have a carbonyl that's directly connected to our benzene ring. So this actually is an electron withdrawing group, which is going to make it a meta-director. Now we're reacting this molecule with reagents of nitric acid and sulfuric acid. So these combined are the reagents necessary for a nitration reaction. Remember that if it is a sulfonation reaction, it would just be H2SO4 all by itself, or fuming H2SO4, but the combination of these two makes it a nitration reaction. So we will be installing a nitro group at the meta position, and since there's only one possibility for the meta position, we will only get one major product. So if we were to put the nitro group here at this meta position or here, it's the exact same product. So this will be our only product. In our third problem, we have a benzene ring with a bromine attached. Now bromine, even though it's a weak deactivator, as we saw with the halogens, they are orthopara directors because they can provide those fourth resonance structures. Okay, so we know that our incoming group will go at either the ortho or the para position. Now let's take a look at our reagents. We have an alkyl halide with a Lewis acid. These are the reagents necessary for the Friedel-Crafts alkylation. Now just to double check our limitations, Friedel-Crafts alkylations do not work with moderate or strong deactivators. Now the bromine is a weak deactivator, so the Friedel-Crafts alkylation will proceed very readily. Sorry, I'm going to modify that last statement a little bit. So the Friedel-Crafts alkylation does not occur when a strong deactivator is attached to the benzene ring. It will occur in lower yields with a moderate deactivator, but mainly with the strong deactivators is when it does not occur at all. But since our bromine is a weak deactivator, it will proceed readily. Okay, so we know that we're going to install a 3-carbon chain, this group here, on our benzene ring in either the ortho or the para position. Let's go ahead and draw both, just so we can see what they look like. Now, even though bromine is a large atom, it's fairly contained. However, the isopropyl group we're installing on the ring is sterically hindered. So even though the bromine may not provide that much steric hindrance, the incoming group may not fit very well. There could be some clash of electron density here. So as a result, again, the major product is likely to be the para-substituted product because you have less steric hindrance. Now, if you're trying to perform an EAS reaction on a benzene ring that has 2 or more substituents, the way that we determine the directing effects is by looking at the strongest activator. So the strongest activator on the ring is the one that controls the directing effect. So in our first example, let's go ahead and take a look at the activating and deactivating abilities of our 2 substituents. So first, a methyl group is a weak activator. So we'll go ahead and label that. Our nitro group is a strong deactivator. Now we want to focus on the strongest activator. So a methyl group, even though it's a weak activator, it's more activating than a nitro group is. That means our methyl group is going to be the one that's controlling the effect of the incoming substituent. Now we know that our activating groups are orthopara directors. Now we'll be reacting this benzene ring with halogenation conditions. We'll be installing a bromine at either the ortho or the para position. Now we want to focus on the ortho or para position in relation to our methyl group. So for our methyl group, we have 1, 2 ortho positions, and our para position is currently occupied by the nitro group. So that means our incoming bromine will only go to the ortho position because that's the only one that's available. So we will end up with a bromine at the ortho position. And you can either draw it here or here. Either way, it's the exact same molecule. Now let's take a look at a similar structure. Again, we have a methyl group, I just didn't write the CH3, and a nitro group, but now they are meta to one another. So we just saw that our nitro group is a strong deactivator, while our methyl group is a weak activator. And since our methyl group is stronger activator than the nitro group, it's going to have the directing effect. and our incoming group, which is bromine, will go to the ortho-para position. Now let's take a look at all of the possibilities. We have our ortho positions here and here. We also have an open para position. I'm going to go ahead and number the carbons, and we'll consider placing the bromine at any of those positions and see which one is going to be the most favorable. So it can be placed here at carbon 2, here at carbon 6. Those are our two ortho positions for our methyl group. Or it can be positioned in the para position on carbon number 4. Now, carbon 2 is surrounded by a methyl group and a nitro group. Now we know that a nitro group has a structure where we have a nitrogen double bound to an oxygen and single bound to an oxygen. So it's a fairly bulky group. So if we were to place the bromine here, we would have a lot of steric hindrance with both the methyl group and the nitro group. So it is unlikely that our bromine will go to that particular ortho position. Now, comparing carbons 4 and 6, if we were to place the bromine here, it would have a bit more steric hindrance with our nitro group. Then, if we were to place it here, it would have less steric hindrance with our slightly smaller methyl group. So this group, or this position, number 4, is unlikely, again, because of steric hindrance with the nitro group. So that's going to leave our last position, carbon number 6. So we'll place our bromine here. Our nitro group will be on its own. And we will get our major product. So this product was formed as a result of steric effects, which are some things you want to consider when you're determining major products with multi-substituted benzene rings.